Welcome everybody. Let me welcome you to the fourth webinar organized by YERME, the group of young researchers within the European Society of Research in Mathematics Education. I am Andrea Maffia. Together with Dorota Lembrer, we are the YERME representatives in the YERME board. Today our speaker is going to be Anna Baccaglini-Frank. Anna Baccaglini-Frank, PhD in Mathematics Education, is an associate professor at the Department of Mathematics of the University of Pisa in Italy. Her research interests include technology-enhanced learning and educational interventions for students manifesting persistent difficulties in mathematics learning. She is a member of the board of the Italian Association of Research in Mathematics Education, and she leads the thematic working group 24 at YERME, the conference of YERME. The title of Anna's intervention today is Navigating the Treacherous Waters of Interdisciplinary Research, Crossing Boundaries Between Mathematics Education and Psychology. Thank you, Anna, for being here with us.
Thank you so much. So I am going to start the presentation. And first of all, I wanted to say how honored I feel as being invited as the fourth YERME speaker at these webinars. And when it was suggested to me to speak about interdisciplinary research, I had very mixed feelings, and I want you to know that because honestly, I don't feel like a super expert in this, although I have been, let's say, navigating these waters for a few years now. But the reason why I accepted to do this, and actually I chose this topic, is because I had you in mind. With you, I mean, I hope that most of you are young researchers, and the talk is intended for you. And basically what I would like to tell you is what things that I would have liked to know some years ago. So this is the spirit with which I prepared this talk. And also I chose three topics, three things to talk about that are explicitly things that I have done research on with some graduate students and colleagues. So they come from my personal experience with all the limitations that this brings. So to describe these navigations a bit further, I am going to introduce myself. Let's see, here we go, with this diagram. This presents my research and the dominant fields that I've touched along the way. So I started with a degree in mathematics from an Italian university. And soon after that, I interviewed before I even finished the degree, and I got hired at the Education Development Center in Boston, where I worked with Al Cuoco and people like Paul Goldenberg on curriculum for high school. And this is where I learned about math education, curiously. And so along the way, while I was working there, I was talked into getting a PhD and master's degree along the way. And I worked again across the ocean, so at a university in Italy and one in the United States. My supervisor in Italy was Maria Alessandra Mariotti, with whom I did my research on conjecture generation in dynamic geometry, and probably some of you have heard a little bit about that. But while I was doing that, I actually was collaborating along the way with, secretly, with a group of psychologists at the University of Padova in Italy. And they wanted to know more about mathematics education, but also they wanted my help on designing tools for diagnosing or assessing mathematical learning difficulties in high school students. So curiously, I started learning about psychology that way. It's a little bit contorted. And then after a brief period with Celia Hoyles and Richard Noss at the London Knowledge Lab, I was, let's say, called back to Italy on a project for elementary school, grades 1 and 2, and preventing persistent learning difficulties in arithmetic. It's called Per Contare. And during this project, I participated to a summer school of the European Dyslexia Association. And because we were working together with them on some parts of the project. And there I met Yannis Karagiannakis, with whom I'm still collaborating on this idea of mathematical learning profiles. And that is going to be in the third part of this webinar. Just to get an idea of the other perspectives, with my first graduate student, and I started a little bit before working with her, Giulia Lisarelli, I picked up the discursive perspective and started looking at how that could be used for our work in technology and learning through technological tools. And my second graduate student was Elisa Miragliotta, with whom we worked on geometric prediction. And I will talk a bit about this because the work started from a detailed analysis of the visual spatial abilities from a psychological perspective. Finally, the Per Contare project got funded again. So right now I'm working on that now for grades 3 and 4. It's curriculum development, inclusive mathematics curriculum development, basically. And my two postdocs are Alessandro Ramplu and Silvia Funghi, whom I thank very much for their feedback on earlier versions of this webinar, as well as Elisa Miragliotta, who helped on the geometric prediction part, and Giulia Lisarelli is helping me on a parallel project for grades 6 and 7, always in inclusive mathematics education. So that's me. And now we can start with the structure of this talk. And I think it's a good idea for you to look at especially these green highlighted things. You can see there are 3 parts: number sense, visual spatial research, and mathematical learning difficulties. We're going to touch on each of them. But the green highlighted things are places in which we will be interacting. So first, there's going to be really soon, there's going to be a first breakout, and you'll get a chance to talk with other people in your group, and I won't be in your group, but then you're going to report back to me. We're going to do it for exactly 8 minutes, and I have a very technological tool here for calculating the 8 minutes in a set of 3, 3, and 2. And all right, and then there's going to be a poll and then a virtual poll. So be ready, and then we'll do question time at the end. Okay, so here we go. Mind the whirlpools. So I'm going to play with this metaphor a little bit, and the whirlpool here indicates possible dangerous terminology, maybe used different ways in different groups. And I'm going to give you a very basic example. If you say mathematics to a mathematician or to a math educator, probably many things come to mind, especially many different domains like arithmetic, algebra, geometry, topology, etc. If you say it to a psychologist, now let's take it generally speaking, they will probably be thinking arithmetic, what we mean by arithmetic, or actually even managing natural numbers only. So it's not a limitation, it's just something to keep in mind so that communication, works between groups. And so I'm going to use this symbol when we have some issues like these potential whirlpools that, might come up. And again, this is from my limited experience, so don't take this like it's not a super reference to famous research or anything. It's just in my experience. Okay. So here we go with the first breakout, and this is my first question for you to work on in your group. I think you're going to get randomly assigned to a working group. And the question is, what is number sense for you? So come up with ideas, and then you're going to report back in exactly 8 minutes.
Welcome back to the main room. It's time now to report to Anna what came out from the discussion in your small groups. To do that, you need to raise your hand. you have a button to raise your hand at the very top of the screen. When you click on that, we can give you the possibility to talk. And so then you can turn on your microphone and report about the discussion that happened in your small groups.
About distinguishing quantity, representing and using quantity, and that also one of our colleagues already worked with that notion, and he mentioned that it was a notion that was difficult to define and that authors do not agree upon that. So that was all we had time to discuss about. Next time will be much quicker.
Yes, that was the idea. So it was to familiarize also with these breakouts, but that was a great start, and that is definitely one of the meanings. Anybody else? I would just like for everyone to hear different ideas that are behind this term.
Can you hear me now? Yes.
Yes.
Okay, sorry. So we had the same issue, and we just could to talk in the chat. But what we said, we had a lot of different ideas, and someone talked about summability in relation to number pattern. Someone has talked about understanding quantity in basic operation.
And operations, that was different from what we had before, right?
Yeah, and with a special focus about basic operations. And,
okay.
And we were, we didn't know if the symbol were linked to the quantity is taken in consideration when we speak about numbers.
That's a very good concern. Good for you. Well, we're going to talk about that.
Okay. And that was all.
Thank you. Shall we hear one last group if we have time?
Cynthia.
So I have very little consideration. I'm in group number 7. We agree that the number sense meaning refers to depends on the opportunities that each person have, and also according to the age. For instance, for kids, number sense can refer to the ability to manipulate objects, in this case numbers, generalizing and manipulate relation and recognize relations. And for adults, for mathematicians, for researchers as well, the meaning is a little bit wider. That's all.
Okay, very good. So these are all things that come up. Andrea, is it okay if I continue now? I'm sure there are other ideas, but the idea was to talk about it and start understanding how many different ideas there are behind this term. And just to give you an overall picture, so here is a table in which I wanted to put two kind of extreme perspectives. So on the left hand side, let's say broader educational perspective really is comprehensive. It includes many, many things. Some researchers talk about a melange of skills. Birch did a really nice review in 2005 talking about what is under this umbrella of number sense. And even to talk about skills is probably limited within this perspective, because researchers have talked about an awareness, intuition, recognition, knowledge, skill, ability, desire, feel, expectation, and so on, related to counting, number patterns, magnitude, comparisons, estimating, and number transformations, as well as, let me include some things about fingers, finger and finger gnosis, and this is what I'm going to talk about in a second. Whereas a very different perspective, much more limited, and this gets at some of what was going on probably in some of your groups, and what we were hearing now about it depends on age and on the person. Well, for neuroscientists, some neuroscientists, it actually means the numerical abilities that are common to animals and humans from infants to adults. So actually, they want to get rid of any developmental issues as much as possible, and even look at what is in common between us and animals. So very, very different ways of approaching it. The neuroscience perspective does this because of also they want to be very operational in the kinds of experiments that they do. They have a much stricter methodologies, let's say, and ways of advancing the field. Or I have to be strict with myself, because otherwise I talk for hours. So I actually have notes about what not to say instead of what to say in these slides. So there also are perspectives in between, and this is going to come up also later. These researchers, for example, talk about processes. They define number sense like this: processes where approximate evaluation of magnitudes or symbols representing magnitudes is used. And here the symbol issue comes up. And it comes up also with ordinality, which is going to be something that we talk about in a second. So symbols are actually quite important, and they are gaining importance in this research. But what do we agree on pretty much across these fields? About some educational implications. One is that number sense is a necessary condition for learning formal arithmetic at the early elementary level, that it is critical to early algebraic reasoning, and you'll pretty much read these kinds of sentences in very different kinds of papers from different fields. But also that number sense is related to using fingers. And I think this is really interesting for counting and representing numbers, yes, but also in more basic ways. So using fingers in more basic ways can have a positive effect on the development of numerical abilities and number sense. And this is a finding that has come up across fields. And it has to do with finger nausea. And I wanted to give you this definition of finger nausea in these terms. They call it the ability to differentiate one's own fingers when they are touched without any visual cues, because it gives you a good idea of how these abilities, are defined very frequently in psychology. Here, psychology is actually building on neuroscience, and their definitions are very operational and very closely related to the tests that are given to test these abilities. So what you see in this picture is one of the tests that are done for finger nausea. And two findings that have emerged over the years, and upon which a lot of research was carried out later, were these. Noel in 2005 published a paper on how finger gnosis tests is a better predictor up to 3 years later after the test than intellectual measures, of numerical abilities. They say mathematical, but numerical. And finding number two is from 2008, she did a really, really interesting experiment in which she found that finger training, not number training, but finger training of this finger gnosis actually had a positive effect both on finger gnosis, of course, but also on numerical performance of these kids. And from this research came then various proposals in the educational fields suggesting to implement finger training as done by Noel, even during mathematics periods in school. And this is actually now being done in some schools, at least in the United States. We thought this was extremely interesting, not only us, but we picked this up in the context of numerical tasks. So, okay, great. Let's use fingers. Let's do various kinds of finger training, but let's do it in already the context of numbers and representing numbers with fingers. And I think Gemma is actually also with us in the webinar. She is the second author of this paper. And we studied this in the context of multi-touch apps. And I'm telling you this because here we worked on a different definition of number sense, and we actually talked about number sense abilities. And here we suggested that for a careful analysis of these, we should take into consideration all of these. This is a table from the paper. Okay, so the most basic ordinal and cardinal aspects of number. Okay, cardinality is what is usually always there, but also ordinality. And ordinality we think is extremely important and actually understudied. And I'm going to talk about that in a second. But also these three areas: finger gnosis and control, subitizing, and representing numbers with one's fingers. So these were aspects that were very important and actually analyzable within this research. So this was our definition and how we operationalized it in the analyses in this paper. I'm skipping from here to there because it's more giving you an idea of things that might come up and can be important. And I mentioned this ordinality and cardinality. So the dominant paradigm in neuroscience is that cardinality is the important thing to go and measure somehow. So you have to assess which of two numerals or which of two collections of dots usually is greater. Okay, and that, you know, coming from the Piaget's line of research has been the dominant paradigm in neuroscience. But this has been challenged by Lyons and his colleagues, who have noticed in neuroscience studies how also ordinal aspects are very important. So children's competencies, they say, with ordinality predict their abilities to do mental arithmetic. And actually in second grade, the ability to assess the relative order of number symbols, and here the symbols come up, you see, is an increasingly strong predictor of mathematical achievement. So definitely more attention is being paid now to ordinality as well. And so let's take a step back. And I think these two things that we've seen until now are examples of transdisciplinary research. What do I mean? That first we looked at how research in neuroscience and psychology on finger gnosis gave rise to some things that happened in education. And now we were looking at how ordinality has influenced this as well. And now more and more researchers also in mathematics education and education in general are looking also at ordinality. And what do I mean by transdisciplinary research? Well, I'm going to use the idea proposed by this Spatial Reasoning study group. The authors are listed down here. These are the authors of a really great educational studies paper, and a new paper just came out a few days ago in Scientometrics, which I didn't know. It's a Springer journal. So they talk about multidisciplinary research as research that aims at combining monologues, whereas interdisciplinary research aims at creating dialogues, and transdisciplinary research aims at sustaining what they call holistic conversations. And the aim here is to, and here I'm going to quote them, to transcend the insights and solutions available from singular disciplinary positioning, so within a certain discipline, while at the same time maintaining the advantages of creativity and initiative peculiar to each specific field of knowledge. Okay, and later on, we're going to see how they address this in the context of spatial reasoning, in fact. And with this, I'm not saying that transdisciplinary research is better. It's just different. And I think it's useful to keep in mind distinctions such as this one between different ways of crossing boundaries, let's say. And yes, I know I wrote interdisciplinary in my title, and this is because it's, I'd say, in my experience, the most common word. And here I wasn't actually meaning this interdisciplinary, I was meaning just crossing boundaries. And if I have to actually define my research as multidisciplinary, inter or transdisciplinary, I'd probably say it's most multidisciplinary at most, but I do have an aspiration, let's say, of becoming transdisciplinary maybe at some point. So, okay, so now we also know about transdisciplinary research. And here a whirlpool about abilities and skills, because this came up probably also in your groups. It definitely came up in this part of the talk where I was talking, and I didn't on purpose define abilities or skills. So what you see on this slide is just my note about, in my experience, what I have come to think when someone says abilities or skill. So ability, I think of, and in my experience, it refers more to basic processes upon which others are constructed. So other processes build on these. And some even of these processes are believed to be innate. There's a lot of debate on innateness, and I don't assume in general innateness, but some people do. And also that these abilities, some of them are developed very early, even before language. So they're called pre-verbal. And this is an important distinction. You can pretty easily distinguish between pre-verbal and verbal abilities that come later with language. So the skill instead is more learnable, related to sociocultural influences and including educational exposure and language, of course. So these are just ways of thinking about these terms. Of course, for many researchers, ability is also learnable. So be careful also about that. It's not black and white. I'm just trying to give like extremes of a spectrum, maybe. So, and be careful, there are many variations of these meanings, but these can be intended. Okay, so this brings us to the second part of the talk. You see, I'm touching briefly upon different things because my goal is not that you learn everything specifically about each of these topics, but more get an idea about the difficulties in crossing these boundaries. Okay, so now I'm going to present another little bit and then get ready to vote and then to work in groups again pretty soon. So here we go with, we talked about number sense. Now we're going to talk about a different set of skills or abilities or whatever. And these are ways in which these spatial somethings have been talked about, spatial reasoning, if we want to follow the group, this spatial reasoning study group that was founded in 2012. And also Natalie Sinclair is part of it. And no, I'm not part of it, but Natalie is, just so you have some reference. Also Joanne Mulligan, for who knows her. So let's see. This I thought was very interesting. It's from their 2017 educational studies paper, and it's a map of research relevant to spatiality in the domains from left to right of neuroscience, psychology, education, and mathematics education, and mathematics and physics. Okay, so they looked at journals in which it appeared, and you can see it's quite diverse. And here, just also to get an idea of the range of people and communities who talk about this, and also over time, it's interesting to notice how the historical emergence of this construct went. And also this might alert you to some dangers. So I'm going to put up our little whirlpool here about difficulties in communicating. So these, if you look into the picture, well, not on my slide, but maybe in their paper or in a blow up of the slide, you'll see how different some of these constructs actually are. And some of them you actually might know. So spatial reasoning has roots all through time and space. And now I'm going to talk about a specific research experience that on visual spatial abilities that was developed during Elisa Miragliotta's PhD work, which is now concluded. And I'm going to use a different metaphor. You can tell I like metaphors. I'm going to use the metaphor of the tunnel of Eupalinos in Samos in Greece. It was a tunnel excavated over 2,500 years ago as a water supply to get water into the island. And it was designed by Pythagoras. And he amazingly was able to very precisely calculate how and where the groups of people digging in one direction and in the other direction would meet inside the tunnel. And it worked. Okay, I think there are only 2 examples, at least Wikipedia told me that there are 2 examples of this in the world. So, and I'm going to use this to talk about research that potentially might meet and become multidisciplinary, at least. So that this is how I connect the work. All right, so here's our tunnel, and we have psychology on the left and mathematics education on the right. And let's talk about visual spatial abilities in psychology but on the other side, we're going to put spatial reasoning in mathematics. So here's our setup, and I'm going to show you now what the psychologists have described as a list of visual spatial abilities. They also provide a corresponding set of tasks, as they always do, tests actually, for each of them. And this is pretty much how they define them, through being able to correctly answer certain kinds of questions. And now I'm going to bring geometry into the picture. How does geometry come into the picture? Well, psychologists think that geometry is the privileged mathematical area in which visual spatial abilities must be exercised and are exercised. And that certainly makes sense for us as well. However, as mathematicians, we know pretty well that visual spatial abilities are used pretty much in any mathematical domain. But let's stay simple and stick to geometry for now. And I thought something curious is how psychologists actually talk about geometry. Again, geometry has different meanings, let's say, for different communities. So here is how a group of researchers who's actually quite active in psychology and visual spatial research defines geometry. They say a student's ability to respond to the typical geometry questions on the mathematics curriculum. And they correlate it, as typically is done in psychology, to visual spatial working memory in this case. And all sorts of statistical analyses lead to these correlations and whatever. But when I read this definition of geometry, I kind of felt like this, because I didn't really know what to think. I mean, what does it really mean for us? What is their idea of geometry? Anyway, so you can see it's complicated, but let's go to Elisa's side of the tunnel, and she started digging, looking at their side. So what she did was to try and think about how those visual spatial abilities are used in geometry reasoning. Okay, so she interviewed a number of students and tried to use those visual spatial abilities to analyze their reasoning in response to these questions that she was asking them in geometry. And 2 of these abilities stood out particularly in her work, in her initial work. And they're these: imagery generation ability, okay, which is described as the ability to generate vivid visual spatial mental images quickly. All right. And imagery manipulation ability, which is the ability to manipulate a visual spatial mental image in order to transform or evaluate it. So, yeah, however, it's not that easy, and providing operational definitions of the abilities within the domain of geometry, which was the first kind of task that we set out to solve, was actually quite difficult. So before telling you why it was difficult, I am going to start the first poll and ask you to exercise your abilities and imagine 2 internal diagonals of a cube. Okay, so they cross through it, and I wonder whether they intersect perpendicularly. Now, some of you I know the task. This has been used in a different form by Fishbein and then by Maria Alessandra Mariotti with many groups of her students. So if you've thought about it, great. If not, just try and quickly decide whether you think it's yes, always, sometimes, or no, never. And okay, great. I think I see you're voting.
people didn't notice it, the poll is now where the chat used to be. So in the right bottom corner of the screen, there you have to select, you can choose only one of the available options. So select the one that better corresponds to what you think.
Don't worry too much, because then you're going to think about it for another whole 8 minutes very shortly. I think you can't see the votes yet, but I'm going to soon end the poll so you can see. It's very symmetric right now, the configuration. All right, since you're going to think more about it in a second, I am going to show you the answers. So we have almost as many yes always is as no nevers, but most people have said sometimes. Okay, so great. And I'm not going to say anything else about this. I'm just going to let you know that different people had different ideas about it, it seems, which is great. And so now I am going to put you in the groups again and ask you to stay with me for a second. Think about it together. So explain your reasoning to the group members. And first of all, explain your reasoning. If you can, and if you're somewhat familiar with the visual spatial abilities, you can also try and say which ones you used. Okay, you're going to get a list of them in your rooms. So, but especially attend to your reasoning and try and see, like, if the visual spatial skills are enough to explain whatever you were thinking. Okay, go. You are back with me. Okay, so I hope that was a fun breakout. And I invite whoever feels like it to share some ideas from you or your group on how you worked it out. So what your final answer was, but also your reasoning.
Yes, me again. So
hello.
I chose the wrong answer, and I explained my reasoning in the group. So what I was able...
What did you choose?
I chose perpendicular, and my reasoning, so I imagined a cube, and I imagined the diagonals, and I know they intersect in the center of the sphere. I don't know the term.
Yeah, see, a sphere came into the picture now.
And I drew analogy from the square. So that was my lousy reasoning. I realized...
No, it's fine. It's very typical. I was surprised so few chose yes.
We had in our group, I don't know what would be the term, but he's not a cheater, because he knew he probably works with someone, and he explained to us, he told us to make to intersect, not to intersect, cut, yes, to cut a cube by its diagonals, and and the intersection is rectangle, so that was enough for me to realize my error. And Jennifer in our group also, she talked about triangles. Probably vertices of the cube and the center of the sphere. Like, what kind of triangles do they form? And also, Mirko was the one who told us about the the cut. He probably answered right, and the three of us all answered always. So that was our group.
Okay, thank you, Anna. That was great, and it showed many different ways of thinking about it. Great. Well, if nobody raises their hand, I will. I have slides for basically visually showing one of the ways of reasoning that Anna was talking about. And it goes like this. So imagine two diagonals. Okay, now I'm going to help myself with a drawing. Then they actually do intersect at a point, and you need to convince yourself of that. And so they belong to a plane. They define a plane, and you can slice the cube on that plane. And then you open it up. You open up the cube, and here it has colored sides so that you can see this is the slice that Anna was talking about. And of this slice, which is a rectangle, you have two sides that are these sides of the cube, and two yellow ones, which are definitely longer because these are diagonals of two of the faces. So there's a factor of square root of 2, which is greater than 1. And so definitely the yellow is longer than the purple. So if I draw in the diagonals, then since it's a non-square rectangle, definitely those diagonals are not perpendicular. But we used a lot of mathematics, didn't we, to think about this, a lot of theory. And okay, so the answer is no, never. There are other ways of thinking about this, but I think this is pretty convincing to those who know enough mathematics. And be careful, because it's very important to know the mathematics, and that's a factor that convinces you or not and allows you to reason or not correctly about this. Indeed, a shortcoming of why was it so difficult to just explain things through the visual spatial abilities and to try and translate these visual spatial abilities to the domain of geometry. We did, but something huge was missing. Something that here I'm going to talk about in terms of, so what is missing? What we call theoretical control. Maria Alessandra Mariotti, who is, let's say, the scientific daughter of Fishbein, talks about theoretical control as the act of mentally imposing on a figure theoretical elements that are coherent with the theory of Euclidean geometry. And where is this coming from? From the theory of figural concepts that Fishbein presented in 93. There's this great educational studies paper, definitely classic. And a figural concept is a mental entity. This is just refreshing. I'm sure most of you know this, but it's a mental entity simultaneously possessing both conceptual and figural properties. And here's where the two parts come in. You have the axiomatic system of definitions and theorems, which here and for us and in this theory is the theory of Euclidean geometry. It could be a different one, but for us it's that. And the figural aspects. So you have these two components that come together in this figural concept. And within this perspective, you can define a geometrical figure as a mental image with properties that are completely controlled by a definition. Whereas a drawing represents only a material embodiment of it. Okay, so this is actually the theory that Elisa drew upon to construct her actually model of a certain process. So what did we do? We singled out these two abilities in psychology. We're back to Elisa Miragliotta's research that's very, very recent, and it is on geometric prediction. So she came up with a different, let's say, type of task and process behind this type of task. It's a kind of geometrical reasoning, and this is the definition that currently is out. Geometric prediction is the process of a generation of a new geometrical object through the manipulation. So here you see the manipulation of its figural elements, and here we're referring to Fishbein, that maintain invariant certain theoretical elements that belong to the solver's knowledge of the theory of Euclidean geometry. So you see also here a layer coming in of the solver's knowledge of a certain theory, which acts basically as glasses in allowing to see or not see certain things. Okay, so here is our setup. And this is what Elisa, was how Elisa was working. And this is, let's say, the fruit of her work. I'm not going to go through the whole model, but this is her funnel model of the micro process of geometric prediction. The metaphor of the funnel is because various things come into play, and I'm going to call your attention especially to the theoretical elements and the figural elements, which are the green and the blue. They come into play and they spit out from the bottom of the funnel the prediction. And then in a problem-solving process, it's likely that many of these processes take place and they feed into one another within a, let's say, macro process of geometric prediction. And this is a model constructed for high school, thinking about high school students' reasoning and actually even university students' reasoning, where there is a clear exposure to the theory of Euclidean geometry. So if we want to think about how this model could be adapted to younger children's reasoning, which is what psychologists look more at, you could maybe think of substituting the theory of Euclidean geometry with maybe intuitive geometrical constructs, as the psychologists say, or maybe different levels of theory as described, for example, in the Van Healy model. These are possibilities. We haven't worked on this, but eventually I think this could be a way of meeting in this tunnel, and hopefully the face of the psychologists, or friendly psychologist colleagues, will look more like this instead of my face reading the geometry definition, which I think they would agree to maybe revise in a joined work that becomes actually multidisciplinary at least. Okay, so yay. We are going to now take a step back and finish this section with what I had promised you, the transdisciplinary definition proposed by the Spatial Reasoning Study Group. They introduce this spatial reasoning as the ability to recognize and mentally manipulate the spatial properties of objects and the spatial relations among objects. So you see that there is this mental manipulation. There are very frequently these dynamic components, but then the spatial properties and spatial relations aren't applied to a specific mathematical theory like the theory of Euclidean geometry. So I think that's a very interesting and good example of maybe differences between staying within a specific discipline and then trying to do this transdisciplinary research. I'm just giving hints here and there at what this might look like. Okay. So now we take a little breathing poll before we move to the last part of this webinar. And this is a virtual poll because it was kind of difficult to set up. So here in the column on the left, you read lots of names of famous, I hope to you also, researchers that are known for things in mathematics education. And I would like you to try and decide if, like, what kind of researcher each one of these is or was. Some is and some was. But you can write in the chat if you feel like it. I was quite surprised. My source is just wiki sources. So I was actually quite surprised myself when I looked them all up. So maybe I'm going to give you a minute to breathe and guess at who was who. Okay, Piaget biologist and psychologist could be. Okay, Vygotsky psychologist. Okay, Vergniaud mathematician, and we have Freudenthal mathematician. All right. Okay. All right, man, you're doing pretty well. And so I don't know how surprised you'll be to see, ta-da, actually, the mathematicians, you identified Freudenthal and Vergniaud as mathematicians. they were pretty much all psychologists, among other things. Relatively few of them are considered by the wiki sources as pedagogists or educators. We have 3 philosophers, and yes, Piaget was also a biologist. So yeah, Piaget was pretty much everything except for a mathematician. So, okay, now that was like a little relaxing breather. And now we are going to finish with the part on mathematical learning difficulties. So these are talked about also in terms of dyscalculia in some of the literature. Where does this label come from? It's interestingly, it comes from studies on children who had low achievement on an arithmetic calculations test. And the way it is used usually in researchers talk and also just everyday talk is usually like this. To have dyscalculia means to have performed poorly on a certain test, but also there is an underlying assumption of attribution of causality of this behavior to a clinical condition. And also, so implicitly, this label, this having dyscalculia, becomes an invariant attribute of the person. And this, of course, has serious implications in education. Okay, various terminology. Some of the dominant terminology is this developmental dyscalculia, if we look at it in the developmental phase. Specific learning disorder, as is presented in the Diagnostic and Statistic Manual of Mental Disorders, number 5 now. Mental learning. Then D in this MLD stands for disability, disorder, difficulty, among others. There is still no consensus. There is consensus about the lack of consensus. And also even only within the more clinical population of the researchers looking at this, there is a lot of debate and lack of agreement about many issues regarding MLD. Also, Lewis and Fisher have a really great paper in the Journal for Research in Mathematics Education, which is an overview of 40 years of research on identifying MLD. So, okay, no consensus. Studying MLD, I have tried with this Greek colleague of mine, Yannis Karagiannakis. And on the side of psychology, basically, we start from the idea of failure on specific kinds of tests. And these need to have reliable tasks and standardized administration. These are typical methodological traits. And it is due to, this failure is due to deficits. The underlying idea is this: in certain abilities or cognitive mechanisms, they call them. And there's also this idea of correlations. There are a lot of studies about correlations between abilities that then are said to predict mathematical achievement. On the other side, we have mathematics education that also takes socio-environmental causes into the picture. And here, many researchers say that we need to make sure to exclude these before we start speaking of disability. Many researchers even don't want to speak about disability or deficit, so that we actually try to avoid the deficit talk as much as possible. And Einat Haid Metsuyanim's work is really interesting on the idea of disabled mathematical identities that actually is also the fault of the teacher. So it's actually a co-construction that happens socially. And it's not the fault of the kid with a deficit. Then we suggest differentiating learning profiles and overcoming this labeling. And we try to find mediational tools, we say many times, and signs with which we can implement remedial interventions and avoid or overcome failure. So it's a kind of different way of looking at all of this. I'm going to come in from the left again. A very, very famous model is this. It's called the triple code model of Dehen, which is used to describe the processing of numbers in adults who have had a normal development. So there are 3 codes: verbal, visual, Arabic symbolic, basically, and analog. And then there is transcoding between one code and the other. This model provided grounding for many studies in psychology and neuroscience, but it has also been the basis for the initial hypotheses on dyscalculia, where an analog magnitude deficit was an original idea, and then there was the axis deficit idea where the problem is in the transcoding, possibly. So those were initial ideas behind dyscalculia coming from this model. And a very different model, just to give you the idea of how complex this whole scenario is this one. And I thought it would be interesting because it's proposed for educators, and it's a reorganization of these core numerical skills with the intent of being useful to educators. And these are the researchers that provided that definition that popped up in yellow when we were talking about number sense, and they have the symbolic and non-symbolic number sense. And they group these skills into four main groups, which are these that you see in the model. So what did we try to do in front of all this research that I just brushed on? We tried to do something that I'm going to tentatively call transdisciplinary. And we started by working, actually Yannis Karagiannakis started this with in his PhD work, to go beyond the specificity of the skills involved in the mathematical domain of natural numbers to include those of other mathematical domains, such as geometry and algebra. And the long-term intent is to come up with what he calls mathematical learning profiles that for now are basically cognitive. One day we hope that they will be also, they will have an affective dimension and also more qualitative dimension in terms of how these students express themselves mathematically. And so what did we do? I'm going to go a little bit fast because I see that we don't have much time, and then I wanted to do a few questions at the end, if you have some. We looked at the skills that were described in the literature, and some are very specific, some are specific related to numbers, some were very general, and there's a lot of research correlating these general skills to mathematical achievement. Just so you know, there are also really nice studies by various people who are active also in mathematics education and probably are actually working very well at the boundaries, better than me. So these are some, and papers on SFON and SFOR, and a new one just came up on symbols, spontaneous focusing on symbols. They're popping up all the time, so really attend to those if you're interested. What did we do? We reorganized what we could of these skills and abilities in psychology, and we came up with what Yannis calls the fourfold model. So core, number, and memory are typically the domains, let's say, contained or aimed at in the tasks used for in diagnostic batteries. And we added the logical, reasoning, and visual spatial domains, which are also quite important if we want to have a broader picture and more dimensions in these profiles, dimensions that are pertinent to mathematics. And I think an interesting finding, and this will be the last thing I say in education that we wrote about here, is summarized by this slide, in which you see two students that had the same exact score on the Greek New Calc test, which is the test for diagnosing dyscalculia in Greece. But as you can see on an early version of the battery that was developed by Yannis with these 4 dimensions, actually you see a very, very different profile for each one emerging, where the student 1 is much stronger on reasoning and visual spatial types of tasks, whereas student number 2 is much stronger in memory. So you can actually see that students that before were identical according to these batteries now can have a profile that can maybe better be addressed educationally as well. So these are teeny tiny steps that we've been taking in this direction, mostly from the left, let's say, of the tunnel. We need to work a lot more in this direction that I was talking about, and this is a long-term intent of ours. So what do I want to leave you with? This is what I was thinking of leaving you with. So this is exciting. Whatever kind of research that crosses boundaries, I think is very inciting and should be pursued, but it can be quite hard. Also, you may not easily find where to publish. At least this is a problem for me frequently and for groups that I'm working with. Also, when working with researchers from different disciplines, try to be as explicit as you can about the meanings behind your words. Do not take anything for granted and try to make them say what they mean as well as much as possible. Compare methodologies, because something that might have been perfect for your work in a specific domain, say of mathematics education, may be completely inappropriate for something interdisciplinary or even transdisciplinary. And then have clear long-term goals in mind, so you don't get too caught up in the whirlpools that pop up along the way all the time. All right, so thank you all so much. And now I'm going to leave you with, just to let you know, I did give you references. These are only the references that were in this talk. And now I think we can do question time.
Would like to invite you to participate in the next coming webinar, which we are going to have the 12th of November at 4 p.m. At 4 p.m. And the expert or the presenter at that webinar is Tamsin Mine from Western Norway University of Applied Sciences. And that webinar is going to be divided in two parts, and is going to be in a spirit, as Anna is saying, we are working on to get even more interactive webinars with you, so you are getting in and are able to interact with the experts. So the next webinar is a continuance of the spirit of polls or questions and interactions with audio, so you can talk directly with the experts. So thank you all for participating in this webinar, and we are exact on the time frame. So thank you all, and thank you, Anna, for taking your time and being here with us.
Thank you all, and thank everybody for having stayed so long with us. It was fun.